We're going to talk about a practical approach to quantum mechanics using matrix mechanics, and what I would like to do is to convince you that using matrix mechanics makes all sorts of sense and to show you why it makes sense. So the first thing that we need is a matrix. In order to make a matrix we need the operator that we're going to be thinking about, we have to be able to write that down somehow, and we have to choose a basis set. Once we've chosen the basis set and the operator, we can then create the matrix, and I'll talk more in a moment about how we do that. From the matrix we can then get various things. We can evaluate expectation values for any state that we choose once we've written down that state in the basis that we've chosen. We can of course calculate eigenvalues and eigenvectors, provided we have the computational or the mathematical ability to diagonalize the matrix. And we can make more matrices, so we can combine matrices to learn more about the system. Now, the most important matrix that we have to think about is the Hamiltonian. The Hamiltonian represents the energy of the system, and is one of the key things that we have to understand. The first thing that we really need to choose when we're specifying a system and thinking about the Hamiltonian for that system is the boundary conditions, because that will set the limits on what we're able to do. We need to think about what the particles are. That will, for instance, change the mass, which will change the kinetic energy of the system. We must think about the potential, and the potential is often what actually defines the problem. So you could imagine that we have a square well potential, a quantum harmonic oscillator, or we could have a group of atoms. We have to choose a basis set. We've described that before. Once we have these four different pieces of information, we can create the Hamiltonian for our system. Of course, we can diagonalize. This is often fairly simple. If you have a relatively small system and a relatively powerful computer, or even enough paper, you can diagonalize either by hand or computationally very quickly. However, often you'll find that the quantum mechanical problems that you want to understand are far too complex to diagonalize. And so we have to use some approximate methods. One of these is the variational approach, which I will talk about in lectures, and I'll record a video cast on at some point soon. Another one of which is the perturbation approach. Again, we'll be looking at this in lectures. It's a very standard approach. Both of these methods allow you to explore a system without doing the full diagonalization of the Hamiltonian, which is often computationally better. And notice that in all these cases we are not solving second-order differential equations. This is a significant mathematical advantage, particularly for extremely complex systems. How do we build the Hamiltonian? How do we get there? Well, we can integrate. This is something that can be done. You choose a position representation, you choose a basis set which you understand, and you simply integrate in order to form the Hamiltonian matrix elements. There are other ways, however. There's an algebraic approach. This uses the properties of commutators in certain systems and allows you to construct the Hamiltonian without doing any integration, any diagonalization, any second-order differential equations. You'll see this for the quantum harmonic oscillator and for the angular momentum of an atom. You can also fit a Hamiltonian. So in the tight binding approach that's commonly used in solid-state theory and variants of which are used for molecules, rather than specifying a basis set, we specify the properties of the basis set. We assume it has certain angular momentum characteristics, and we fit the Hamiltonian elements to known experimental data and introduce some kind of distance-based variation that we can understand. And from that, we can predict the results of a system. That can actually be an extremely powerful approach. So, the way that the matrix mechanics approach works is to choose the system we've got to solve, to specify the basis that we're going to use, to build a matrix, and then to explore the properties of the system using that matrix. Well, why not do all of this using position representation? Well, first of all, because you can choose a mathematically easy basis for matrix mechanics. You can do all of the mathematical operations rather trivially and create a matrix that way. With matrices we can do a great deal of computational work. We can use a computational approach to understand how the system behaves and to do all of the hard lifting. And it also opens up various approximate methods, which of course we can do with a position representation, but quite often require the very matrix elements that we've been talking about. We'll see specific examples of how matrix mechanics is used but I wanted to give you an overview of the approaches and the ways in which it can be used to explain and motivate this new approach.